Hello and welcome to what's the final video in this series of graduate classical mechanics videos. There might be some in the future, but for now, this is the end of the first course. We'll end up with this crowning glory of a problem, which is the application of Hamilton-Jacobi formalism to what's known as a linear Stark effect. So the Stark effect is actually a quantum mechanical effect. So it happens when you have a Coulombic potential subject to an electric field in the following manner. You have an electron. In the most general case, the electron is relativistic, but in this particular instance, we'll take it to be non-relativistic in a potential that's given by the Coulombic term plus a electric field times Z. So if you take the gradient of the potential, you're going to get basically the electric force, which is going to be a constant electric force along the Z direction. We're not worried about the charge of the electron or the mass or anything like that. So we're just keeping things simple. What we wish to do is to solve this equation using the Hamilton-Jacobi formalism. This was first done by the great German physicist Karl Schwarzschild. And in case you're wondering, yes, it's the same Schwarzschild of the black hole event horizon fame. He was the first person to solve Einstein's equation for a spherically symmetric star, which was later identified as the solution of a black hole, actually. He did not know that he was solving a black hole equation around 1916. And he did this while he was engaged in trench warfare, the most brutal kind of infantry warfare in World War I. He did both the Schwarzschild solution as well as the linear Stark effect in battle conditions. And shortly thereafter, he died while World War still was raging at that time. A pretty great human being. So read up about Karl Schwarzschild if you can. Later on, I'll tell you more about the other people who contributed to this problem. But right now, our aim is to actually solve the Hamilton-Jacobi equation. Let's recall what it is. The Hamilton-Jacobi equation is a partial differential equation as follows. S is some arbitrary function known as Hamilton's characteristic function. So this is known as the time-dependent Hamilton-Jacobi equation because it explicitly depends on time. So S is the Hamilton's principal function. So if you think about it, QIs are just the positions. Del S by del QI are the momenta. So S, if you differentiate S with respect to the variable QI, you're getting the momenta of the system, comma T plus the partial derivative of S with respect to T. When you add it to the Hamiltonian, you get 0. But this is exactly the kind of equation that the generating functions satisfy. So we can identify S as a generating function of actually type S F2. Now, a simplifying assumption. So if you want to get some clarity about what I just said, you should look at the previous video where I introduced the Hamilton-Jacobi formalism. That's GCM27. Please do see that. And for further clarity, you also have to see GCM26. So this sort of builds on those two videos. So please see those videos first if you have not seen those already. If S turns out to be, if the Hamiltonian turns out to be time independent, so let's say the Hamiltonian is time independent, which it would be in this case, then we could write this in a slightly nicer way. So we can write S, which is a function of Qi, the momenta, which I'm going to call alpha I, t, as W of Qi alpha I, with the understanding that these alpha i's are just alpha 2 up to alpha n, and then you can isolate alpha 1 to go along with time. So you can write it like that. So secretly, we know that alpha I are the new momenta. So the idea behind the Hamilton-Jacobi formalism is that you start with some initial conditions, the system at time t naught, and then in order to go to general time, you create a canonical transformation that takes you from here to there, and in the process also solves the problem. So that's the general feature of this approach. Now, if you put this particular principal function back, incidentally, this object here is known as Hamilton's characteristic function. If you put this thing back in there, then the equation that I would end up with is when I do del S by del T, I'll just get negative alpha 1. And you should identify this alpha 1 as energy, because energy, when multiplied by time, has got the same units as joule seconds, which are the units of angular momentum, and the units of S are angular momentum. This is also called the action. And the units of S are always joule seconds. So alpha 1 plus the H this time, depending on Qi del W over del Qi, because now only the W's have Qi's in them, but no time, is equal to 0. So this immediately tells us that H of Qi del W by del Qi is equal to alpha 1, which is a constant. So this is known as the time independent Hamilton-Jacobi equation. So in this particular lecture, I'm taking the viewpoint that Hamilton's equation is somehow God-given, and we are trying to see what is this mysterious object that's landed on our lap. So we notice that W is a generating function. So let W of the old coordinates and the new momenta be a generating function of type F2. Then we can write Pi equals del W by del Qi, and Qi equals del W over del Pi. And the new momenta are all constants of motion, because they are given by alpha 2, which is equal to P2, alpha 3, which is equal to P3, and so on, up to alpha n, which is equal to Pn. Meanwhile, I can write down what this is, because I know that they are constants of motion. I can write Qi's as del W over del alpha I. So I can identify my transformed Hamiltonian, or the Hamiltonian K, as simply equal to alpha 1, because that is a transformed Hamiltonian, since the time derivative doesn't exist. That thing itself is a transformed Hamiltonian. So now we can write the new equations of motion with respect to the transformed Hamiltonian. Capital Pi dot equals negative del k by del capital Qi. Well, that's equal to 0 because k doesn't have any Qi's in it. So we automatically get Pi equals alpha I for I not equal to 1. So that's as advertised. The momenta are all constants. So we're justifying in a roundabout fashion why we can identify these alphas as momenta with respect to this new Hamiltonian, or as it's called, the Hamiltonian. The other Hamilton's equation, which is Qi dot equals del k over del Pi, is just del k over del alpha I. And since k is equal to alpha 1, this is equal to 1 if I equals 1 and 0 if I is not equal to 1. So Q1 is the only one that's got a non-trivial solution. So Q1 dot is going to be 1, which means Q1 equals T plus beta 1. And Q1 is just from here, del W by del P1, which is alpha 1. So we have this really interesting result that one of the coordinates, Q1, is trivially integrated. Now, what about the remaining Qi's? The remaining Qi's will just be beta I, which is the partial derivative of W with respect to alpha I, for I is not equal to 1. All right, now what exactly is this W? It seems like this W is a mysterious object, and so it might be a good idea for us to interpret W before we move on to solve the concrete problem at hand, which is a Stark effect. So let's interpret the characteristic function W. An interpretation is got by taking the total time derivative of the characteristic function. I do dw by dt. dw by dt is del w by del t. Well, that's of course 0, because w doesn't depend on time. W is just function of qi's and alpha i's. Then you have plus del w by del qi dot. Well, del w by del qi is just these pi's. So I'm going to get pi's times qi dot. Now qi dot is none other than dqi by dt. So I can write this as dw equals pi dqi. And so w is just going to be the integral of pi dqi. This is the old, what's called the Bohr-Sommerfeld action. In the old quantum mechanical theory, it's the Bohr-Sommerfeld action, which when integrated over a closed cycle, that was said to be quantized. So you would see in old quantum textbooks, things like this. If you go around a closed cycle C of PdQ, it's going to be n times the quantity h bar, where h bar is h over 2 pi, and that's how the angular momentum was quantized. So it should bring back some quantum memories in those who have taken quantum mechanics. All right, that's so much for the background. Now let us actually solve the problem at hand. The problem is to solve the Hamilton-Jacobi equation in parabolic coordinates after first separating it. Before we do anything, we have to find a metric in these coordinates. So let's find the metric first. The metric tells us how the distance behaves in those new coordinates. Well, the Cartesian metric is our starting point. So let's use the Cartesian metric. ds squared equals dx squared plus dy squared plus dc squared. X in our case is u to the half v to the half cosine phi. Y is u to the half v to the half sine phi, and z equals 1/2 u minus v. Those are the transformation equations. I've taken it from here. Now, all I have to do is write dx, dy, and dz, and then square them. Well, that's just a lot of algebra. Let's do it. So dx is del x by del u, which I'll write as x sub u. So my new notation is going to be etc. Carry out the mathematics. When I differentiate x with respect to u, I get 1/2 u to the minus 1/2. Everything else remains the same. Then I differentiate x with respect to v. Lastly, x with respect to phi. Now, when I differentiate with respect to phi, I'm going to get a negative sine phi. Now let me square it. So when I do dx squared, then I have to square this one. Then I have to square that. There are 3 more terms because what we are doing is using a plus b plus c squared equals a squared plus b squared plus c squared plus 2ab plus 2bc plus 2ca type of formula. Keep that in mind. So doing the 2ab. When I do 2ab, u to the half and u to the minus half cancel out. V to the half and v to the minus half cancel out. I just get cosine squared. And that 1/4 gets multiplied by 2. So I get 1/2. Then when I get 2bc, 2bc is this and this. So I get a negative sign. And then 2ca also will give me a negative sign. And the 2 will go away. So I'm going to get, also observe, the v goes away when I do this. And when I do that, the u goes away. So let me do this and this next, this and this. And then this and this. All right, that was dx squared. We're going to repeat the same process for the remaining two terms. And then when I do y with respect to phi, I'm going to get cosine phi. Then I square it. And then I have these cross terms. I lose my u and I lose my v this time. So the first cross term is just going to be half sine squared phi du dv. And then the next cross term will be this and this. So I lose my v. And then lastly, when I multiply this with that, I lose my u. We label these equations. I'll call this 1, I'll call this 2. Z, fortunately for us, Z is a little bit easier than X or Y, so this will take a little bit less time. Observe that Z does not even have a phi term, so we'll just have two terms to deal with. Well, Z sub u is just half, and Z sub v is minus half. So when I square, I'm only going to get a plus b, the whole thing squared. So it's a squared minus 2ab plus b squared. Let's call that equation 3. Now we need to add 1, 2, and 3. So my hope is that a lot of these terms will cancel themselves or add nicely. So when I add dx squared and dy squared, you notice that you have a cosine squared there and a sine squared. Cosine squared plus sine squared equals 1. So that's nice. Similarly, and then I'm going to get hopefully a bunch of cancellations for some of these cross terms. Well, the uv term, let me use more colors here. The uv term will again add, because cosine squared plus sine squared equals 1 again. And then let's see what else happens. Here, the du dv term also adds. This term flat out dies. So I'm going to lose that term. Oh, wait. Was I too hasty? No. You do lose it. Here it's cosine phi sine phi. There it's sine phi cosine phi. So you do lose it. And then you also lose this term. So not bad. Quite a bit of simplification results. So let's write the new metric. So that's the orange. And that's a red. And that's the green. Then I have the blue. That's all I get from 1 and 2. And then I have also dz squared. So let me add dz squared. That is well, what do I see here? I see that there's yet more cancellation. This term exactly cancels that. So cross terms are completely out. That's the beauty of the parabolic coordinate system. So it's almost tailor-made for this problem. The separability of Hamilton-Jacobi equation is the key to solving it as a viable partial differential equation. And very few equations are separable. This is one of them. And so this is one of the acute problems in Hamilton-Jacobi theory, because problems can otherwise be quite intractable and you have to go to the computer. So this is what I have. Let me rewrite my result at this point. So ds squared, just the combine the terms together. So I have two terms involving du squared, so I'll combine them. I have two terms involving dv squared, so I'll combine them. And then I just have the one term involving d phi squared. Observe the interesting structure of v by u versus u by v. And in case you were wondering why this whole production to find a metric, the answer is to find the velocity, of course, because the speed of a particle is ds by dt. So the speed squared, which we need to find the kinetic energy, is ds by dt squared. And that's where the metric will help us. So we have to just write this. du by dt squared, which I'll write as u dot squared, following Newton's notation. Newton said that time derivatives should be written as dots. Now we have that, and the Lagrangian can be written. The first step in forming the Hamilton, first step in solving a problem using the Hamilton-Jacobi formalism is write the Lagrangian and then the Hamiltonian, and then we move on from there. So we are not even in the first step at this point. So L, which is going to be 1/2 mv squared minus q times v, that's the way the Lagrangian is written. It's the kinetic minus the potential, where q is the charge of the particle. The v here is k squared over r, and then plus E naught times z. So I'm going to remove this out of my view because I'm done with all the hard stuff. So when I write this potential, it's going to be E naught times z, but z is equal to all that. So actually this works out nicely units wise because E is volts per meter, and this whole thing is meters. So potential is in fact measured in volts. So the thing I want you to notice is that the potential is in volts, means to get the potential energy, you have to multiply it by charge, because charge times volts. Volts is joules per coulomb, and charge is in coulombs. So Q times V is coulombs times joules per coulombs, which gives you joules. So just keep all that in mind, because you will be setting. By the way, the charge Q is the electron's charge, so Q should be set equal to minus E, where E, as everybody knows, is 1.6 times 10 to the minus 19 coulombs, the magnitude of the electron's charge. Now, what is this R? Well, that's another production, right? Because R is a square root of x squared plus y squared plus z squared. It's a magnitude of the position vector. So now we have to find what that is. X squared means I square that. Z squared minus uv over 2. So I'm squaring 1/2 u minus v. That also is under the square root, by the way. I ran out of space there. So this sine squared plus cosine squared is 1. So that just gives me uv plus 1/4 u squared plus 1/4 v squared minus uv over 2. Well, there's a uv there, and there's a uv over 2 here, so we can combine them together. So this gives me the square root of 1/4 u squared plus uv over 2 plus v squared over 4. Now what I'll do is I'll take a half outside. When I do that, I'm going to get u squared, because the square root of 1/4 is 1/2. And then here, if I have to take a half outside, I have to multiply the numerator by 2 first, because I have to write this as 2uv over 4 and then take the half outside. And then here I can take the half outside directly. Well, what is that? That's a perfect square. So you see the miracle? That's half times the square root of u plus v whole squared. So this is just u plus v divided by 2. Now, when you do something like this, you have to be careful because you have the plus or minus possibility, but r is bigger than 0, so we're justified in keeping the plus sign. Beautiful. So the effective potential can be written as, because of that minus sign there, I'm going to get negative. So one thing here is I have to multiply this k with also the electron charge. Okay, because when I do this effective potential, I have to multiply both this and this by the electron charge to get the potential in volts. So that Q is hidden. I'm not writing that in the Lagrangian. So effective potential is negative k squared E over 1/2 U plus V, that's the radius, minus E times E naught over 2 U minus V. So the separability of the Hamilton-Jacobi equation, along with these nice features, will ensure that this problem can actually be solved rather nicely. Now, before we form the Hamiltonian, we have to find the canonical momenta. So let's do that. So first, now we finished writing Lagrangian. Now we have to do the Hamiltonian. So let's write do the canonical momenta next. So the first thing we'll do is find the momentum with respect to u coordinate. That's going to be del L by del u dot. So the Lagrangian with respect to u dot, keep in mind that u dot comes with velocity squared. So I have a u dot squared, I have a v dot squared, and I have a phi squared. Don't confuse this v with this v. This is the velocity vector. Maybe I should write that like that, because there are two v's. I've taken care to write this v as a plain v, but then I started writing it as a curly v, which can be confused with that. So I'll put a vector arrow to remove all misunderstanding. So I have del L by del u dot. So that's going to give me that m is there, but there's a u dot squared. So when I differentiate, I bring the 2 outside. Okay, so when I bring the 2 outside, it cancels that half, but you still have a 1/4 left. So I get m over 4 v over u plus 1 u dot, which tells me that u dot is none other than 4 times p sub u times u over, I'll write, okay, I'll do one more step here. I'll write this as m over 4 v plus u over u times u dot, and then I'll cross multiply both sides to solve for u dot over m times u plus v. So that's my equation expressing the velocity u dot in terms of momentum p sub u. Similarly, let's find what the momentum p sub v is. It's m over 4. This time, I'll get u over v plus 1 v dot. So when I solve for v dot, I'm going to get 4 dv v divided by m times u plus v. Lastly, I get p phi, which is del L by del phi dot. Well, when I take the derivative with respect to phi dot, I'm going to get this 1/2 there. So that takes care of the 2 from that. And then I have uv. So I get m times uv phi dot, which I can solve for phi dot. Now we form the Hamiltonian. Once we have the Lagrangian, the Hamiltonian can be formed if we mistake to say the Hamiltonian is 1/2 m velocity squared plus qv. That's only true if the energy is conserved, which it may or may not be in this case. So we don't know. It's always better to play it safe and write the Hamiltonian from first principles. So it's u dot pu plus v dot pv plus phi dot p phi minus the Lagrangian, with a Lagrangian moreover written as a function of u, v, phi, u dot as a function of pu, pv, p phi, and similarly v dot and phi dots as functions of pu, pv, and p phi. I'm not writing that. The Lagrangian is not a function of time, so we won't bother writing that. So that's the scope of our task. So let's write down the Hamiltonian. When I multiply u dot, which is right here, with pu, I'm going to get basically just square the pu there. Similarly, I'll just square the pv over here. And then square the p phi. Minus the Lagrangian. The Lagrangian is 1/2 mv squared. So that's 1/2 times 1/4 is 1/8. I'll start writing this as u plus v divided by u. U dot squared. But u dot squared has to be written as the square of this thing. So 16 pu squared u squared divided by m squared u plus v squared, running out of space there. And then similarly, I get negative 1/8 from this term. M times u plus v divided by v dot squared, for which I have to write that. 16 pv squared v squared over m squared u plus v squared. Okay. And then I have this term uv times phi dot squared. So, but it's a negative L. So it's going to be negative. First, I'll do 1/2 m times that. And then I'll do the phi dot squared. All right, now here I have minus q times v, so it's going to be minus the effective potential. So I'll just make it plus the effective potential. All right, let's simplify this. When you have 8 and 16, you'll get just 2. So interestingly, 4 minus 2 of the same thing, because u plus v will cancel with u plus v squared, a u will cancel with u squared. So I'm basically getting and an m will cancel with m squared, and the same type of things here. So it is 4 of p squared u, pu squared u over m u plus v minus 2 of the same thing. 4 minus 2 is 2. The next term is similar. And here I have p5 squared over muv, whereas here I have p5 squared over 2 muv. So the difference is going to be p5 squared over 2 muv. And then plus v effective, which is right here. I'll take that 2 upstairs because half in the denominator becomes a 2 upstairs. All right. That's the Hamiltonian. Now, what we'll do is we'll calculate the momenta pu. This is going to be the derivative of the Hamilton's characteristic function with respect to u. PV is going to be the derivative of s with respect to v, and p phi, or principal function, I said characteristic, I meant principal, del s by del phi. Now what we're going to do is we're going to substitute this in the time-dependent Hamilton-Jacobi equation, which is this very first thing I wrote there. So let's do that. Plus the Hamiltonian, which is all of this stuff, except with positions as it is. For the momenta, you put del s by del qi. In other words, you substitute these things for the momenta. And there's no time. So let's write out all this. There is a 2 over mu plus v, at least in the first 2 terms. But there is not, and there's that in this term, but there's not there in this term, and it's not there in that term. So we'll repair the damage by appropriately multiplying them with u plus v in the numerators. And also in these cases, we'll also multiply m in the numerators because there is no m either in these terms. So let's put a big parenthesis. U times pu squared, which is del s by del u squared, plus v times del s by del v squared, plus here's where we need to make the repair the damage. I've taken a 2 outside in the numerator, but there's a 2 in the denominator. Well, to compensate for that sin, you have to put a 1/4. And then I've taken a u plus v in the denominator, which never existed in the first place. So then I have to write u plus v in the numerator. So when I write u plus v in the numerator, I'm going to get u plus v over uv. Well, that is just 1 over u plus 1 over v. And then I get del s by del phi squared, because I'm writing for p phi, I'm writing del s by del phi. Then what about these? I've taken 2 over u plus v, but m was not there to begin with. So I'm left with m e k squared. And then here, I did not have either an m or a u plus v, nor a 2. So there I'm going to get m times e naught over 4. And then I'm going to write u plus v times u minus v, also known as u squared minus v squared. Close big bracket equal to 0. That, folks, is the Hamilton-Jacobi equation for the linear Stark effect. Okay, we've come a long way. So although you won't know it, I'm going to take a short break and I'll return after I come back in about 10 minutes. So we have come to this really interesting point. That's the time-dependent Hamiltonian-Jacobi equation. Now, earlier I told you that if the problem is not time independent, if it's independent, then we can make simplifications. That's what we'll be doing now. So let us, the rate of change of S with respect to T, according to my earlier introduction to the Hamilton-Jacobi method, I called it alpha 1. So I'm going to do that same thing here. In fact, it's negative alpha 1. As a matter of fact, I can create the following ansatz or assumption. I also noticed the Hamiltonian, the original Hamiltonian, did not depend on phi. It depended on u and v, but it did not depend on phi. So we assume the momentum to be conserved in the phi direction. So we can have a separability ansatz as follows. S shall be set equal to negative alpha 1 times t. Well, that makes sense because the partial derivative of s with respect to time is precisely negative alpha 1 as we wanted. And then alpha phi, the conserved momentum in the phi direction, times phi. Plus, we're going to assume that there's a Hamilton characteristic function that only depends on u. And then there's a Hamilton characteristic function that only depends on v. So this separability ansatz actually works in the parabolic coordinate system. That's the entire reason to be in the parabolic coordinate system. All right, so let us work this. Our Hamilton-Jacobi equation, which is this thing, I'll transfer the alpha 1 to the right side. So I'll end up getting, therefore, 2 over m times u plus v u times, when I take the partial derivative of s with respect to u, I will only involve the function w1. So it's u times w1 prime squared. Henceforth, prime means the derivative, the ordinary derivative with respect to the variable. For example, w1 prime means dw. So here's my key. w1 prime means dw1 by du. w2 prime means dw2 over dv. So then I have that, and then the next term is v times w2 prime squared. And then I have this term, which is 1/4, 1 over u plus 1 over v. Del s by del phi, well, that is just alpha phi minus mek squared minus me e naught over 4 u squared minus v squared, close big bracket, equal to alpha 1. Well, what I can now do is separate. Separate means we bring all the u stuff to one side, all the v stuff to one side. Let's see if I can do this. Actually, I can, because observe, I can write 1 over u plus 1 over v as, again, so, okay, one thing I'll do is I'll multiply both sides first by m times u plus v and divide both sides by 2. Let me do that first. So I get u w1 prime squared plus v w2 prime squared plus alpha phi squared over 4u. I'm going to simplify everything down to the most basic terms. And then I get minus of a minus or plus. And then I've taken out these things and brought it to this side. So I'm going to get m times alpha 1 over 2 u plus v, which I can write as u plus m times alpha 1 over 2v. The reason I am separating out to the atomic constituents is because now I can write all the things involving u in one side and all the things involving v on the other, on one side. So let's do that next. U w1 prime squared plus, I'll underline all the terms involving u with orange. And even though I don't have to, I'll underline the terms involving v with red. I'm sorry, I underline all the terms involving v with green. Well, what about this quantity MEK squared? That's a constant. The constant can live either with the u's or the v's. All right, so that constant can make up its own mind of where to live. So I'll just let it live with the u people. So all the oranges to the left. And this, when you bring it to the left, you get a negative sign. Okay, and I said that the constant, which I'll underline with blue, since it doesn't belong to any camp, it's neutral. I mean, if I really wanted to be crazy about it, I could write it as MEK squared over 2 minus MEK squared over, and take half of it over there, but I'll just leave it like this. MEK squared on this side. So I have 5 terms on this side, and that's equal to all the other stuff on that side, all the greens. Well, there's one green that's already there, so I'll write that first. To bring the other greens, I have to change their signs. So when I bring this one to the other side, it acquires a negative sign. That I bring to the other side now. And then I bring that to the other side. Well, if this only depends on u and this only depends on v, then each of them must independently equal a constant. Now, this constant can be called anything you want. I'll call it alpha 2. Okay, so each side is a constant that can only depend on u, that can only depend on v, and u and v keep changing as the particle moves around in this new coordinate system. U and v keep changing. So the only way this can be true is if each side is independently a constant, and that constant I'm calling alpha 2. Alpha 2, as far as we know, can be any real number. So we can solve this for W1 prime. The solution for W2 prime will be very, very similar. So first I'll solve for W1 prime. There's only one term with W1 prime, so bring everything to the right side. So what I'll do is, I know there's going to be a giant square root because that's W1 prime squared, so I'll put a giant square root first. And then alpha 2 over u. And then when I bring this to the other side, it becomes negative alpha phi squared over 4u squared. And then when I bring this to the other side, it'll become plus, right? Well, first I do me squared, mek squared. That becomes a plus. And then when I take the negative to the other side, it becomes a positive. But u squared is divided by u. And then I'm taking negative mu alpha 1 to the other side. So that's becoming positive. And I'm dividing by u. So positive m alpha 1 over 2. That's what I get. I'm going to write this, simplify it a little bit. So I can combine alpha 2 and mek squared because they both have a single u in the denominator, and the rest of the terms are fairly unique. So I'll write them as they are. I'm just going to call this f as a function of u because I'm not going to actually bother doing all the mathematics. I'll indicate the steps. If you're interested in the full details, you can, of course, look at Karl Schwarzschild's great paper. But I'm mainly giving you the flavor of this problem, since doing this problem in full detail will take several hours. So once you have W1 prime equals f of u, you can immediately find W1. It's the integral f of u du. And then I won't indicate it. You can pretty much see how W2 will work. You take all the stuff to the other side and divide by v. You get similarly W2. So I'm going to write W2 prime equals g of v similarly. Okay. So then I get integral g of v dv for W2. So in principle, we have W1 and W2. The important thing is we don't really need to find these w's because it's only the partial derivatives of w which really matter, because the new momenta are got by taking the partial derivatives of w with respect to the alpha i's. So when you do the partial derivatives, it's that integral that you need to find, not the original integral. So but these integrals can be evaluated directly. It's not very difficult. For example, just to show you that I'm not really trying to run away from this problem, these integrals are actually quite elementary. If you write f of u as something like this, au squared plus bu plus c over u for constants a, b, and c, you can identify what a, b, and c are quite easily. So it's going to have that form. It's going to have the form square root of AU squared plus BU plus C. And similarly for G, you're going to have different A's, B, and C, of course, but a similar form. So how can you do a problem, an integral like this? It's not very difficult. So I'll just indicate to you how to do this. So I'm going to get, I'm going to call capital X AU squared plus BU plus C. So integrals of this type are found in this delightful little book known as Peirce, a short table of integrals. It's a very slim book, but it's got all the coolest integrals in the world. And all of them are very doable. Peirce even tells you how to do them or what substitution to use for them. So this integral I found done in this book of Peirce quite readily. So since my x is equal to that, square root of x is that, according to Peirce, this is just the square root of x plus b over 2, the integral du by root x plus a integral du over u root x. And then this part you can do just, this is not according to Peirce, this is according to common sense. That's what you get. And then each of these integrals can be looked up in Peirce. So from the book of Peirce, I get integrals of this type are 1 over root c natural log of root x plus u root c plus b over 2 root c if c is bigger than 0, and it's equal to negative 1 over square root of minus c arc sine 2cu plus b over the square root of minus q if c is less than 0, and here q is 4ac minus b squared. Okay, the negative of the discriminant. Similarly, according to Peirce, so whenever I'm using the reference for Peirce, I'll put a dagger symbol. Integrals of the form du over u root x are solved as follows. This is 1 over root a natural log of root x plus capital X plus root a, where capital X is that, over u plus b over 2 root a if a is bigger than 0, and 1 over square root of negative a arc sine bu plus 2a over u root negative q if a is less than 0. Observe that if a is less than 0, then negative q is positive. So there's nothing wrong with putting a negative q onto the square root sign. And if that's similarly for W2, you can do the same type of things. Once you have that, the entire process is finished, and you can get the beta 1 del S by del alpha 1, beta phi, which is del S by del alpha phi, etc. You can get those and complete the program of the separability. So how do you transition from this classical Stark effect to the quantum Stark effect? There you must be very careful because the operators in quantum mechanics don't commute. So when you're forming the Hamiltonian, you must use a proper operator ordering. So if you want to ever take this to the quantum realm, you have to be super careful. So let me just give you a few historical remarks. These coordinates, the parabolic coordinates, and the separability of the Hamilton-Jacobi equation in the parabolic coordinates was first done, all the initial stuff we did the metric and so on, was first done by Jacobi. Jacobi solved both Kepler problem and the Coulomb problem using these coordinates. The Stark effect itself, as I said, was done by Karl Schwarzschild of the Event Horizon black hole fame. And he soon died of some diseases he contracted after getting injured in the war. So anyway, I hope you enjoyed these long series of videos, especially this particular one. I'll see you in another video.